So welcome to the seminar today, everybody. And it's a great pleasure that Wilke has agreed to give a talk here. And he's going to tell us today about his studies on the steady state formation and holography. And among the many, many things that he is doing, this is certainly only one of the exciting things that in out of equilibrium holographic systems that is going to that he's going to talk about today. But maybe he's also going to tell us other things if he has time. So let's get started as soon as possible. So over to Wilke now.
Yeah, well, thanks very much. Also, a pleasure to give this seminar in Chennai virtually. Hope we can do it in real life at some point. Yeah, so this is really about this. Well, most of the talk will definitely be about this non-equilibrium steady state. This work from March this year with mostly with Christian Ecker and also Johanna Erdmenger. And okay, the final 5 slides I might advertise a little bit. This paper you put out a month ago with Jorge and David. This is a similar kind of setup like in holography, but then it's like the sitter, the QFD on the sitter. Whereas the main part of the talk is just flat space, strongly coupled QFDs in holography. To give you a slight teaser, I put here kind of this kind of results, like what this non-equilibrium steady state will be, which is really like, okay, you have like energy density here. So there's like a cold bath and a hot bath. So high energy density, low energy density, and time goes this way. So you start just with hot and cold, basically together, like at the contact point. And then of course what will happen is that the energy will flow from the hot bath to the cold bath. And then really the problem is how this happens. And yeah, what you then actually will see, I mean, so I won't say much more about it, of course, is that there will be actually a constant energy density in between them, which flows. So, I mean, maybe I should have put arrows here for clarity, that there is actually a fluid velocity. So it's really, it is a fluid velocity towards the cold bath. And something similar, but a little bit more complicated happens for charge density. So I may say more about it. And you can already kind of see here a little bit some of the points is like, this is more like a shock. So it's very short wavelength, and here it's more like a rarefaction wave. So I'll say more about that too. Yeah, and please, yeah, if it is good, I don't like the Zoom seminars too much in the sense that there's usually a little bit less interaction, but please interrupt me at any point if you feel clear. And yeah, I would really appreciate it if there are questions. I can actually see your videos if you on the other screen if you can say something. Yeah, so it's the outline. So this is hot-cold interface, and we included also charge in this work. Question like how does it evolve when you start this at T equals 0? It's basically an initial condition problem or a Riemann problem in hydrodynamics. So I'll first say a little bit about the setup and this very old problem. So this Riemann problem, if you focus on hydrodynamics, and then later on, of course, we go to like holography and strongly coupled QFDs and go much beyond hydrodynamics. And yeah, I'll show you a bit within this Riemann problem. It's already these shocks and rarefaction waves. So we already showed that first, and then really go to this holographic setup. Well, very, very brief points like how to do this numerically. I mean, there are several references, and I've studied like, I mean, this is all based on this kind of shock wave collision. So it's very similar numerical code, but then instead of putting shock wave collisions, you put this hot cold bath. So it's, in that sense, it's very similar. I didn't want to kind of go into the shock wave things, but I'll say a bit about it. And then, of course, there are many kind of, what is it, kind of numerics, like it's far from equilibrium parts. So in that sense, there are many figures and basically the far from equilibrium results. And as I said, and if I have time and if there's interest, I can do a small advertisement of this recent work where you have like study more like the sitter cosmology with gravity in the boundary of T. Good. So for the setup, so I think yeah, already kind of said. So the initial conditions are basically so you just at T equals 0, you have like a cold bath and a hot bath, and it's energy density C and E hot, and charge density is same, so left right. And well, first actually people when studied this, it was a bit of the simplest thing you can really try to do is what's called a double shock ansatz. So you really have like and then within ideal hydrodynamics you can just solve it. So you would have like ideal hydrodynamics basically means that well, we only, there could be d dimensions here actually. So this is more, you really think about this as a factor of the d mu. So, and then cs squared, in our case, we actually only work typically in 3+1 dimensions. So cs squared is 1/3. And because it's conformal, will be traceless, at least for all the results I will show you. In this case, you don't have to assume that. So the cold bath is diagonal, you see, and then the hot bath is also diagonal with also some hot energy density. And then the assumption is that there is this steady state region with these two shocks. So basically, the energy density as a function of at some snapshot as a function of time, or here in rescaled coordinate x/t. You would just have like a steady state region, and then it with a shock would go towards this the initial condition basically. And in that case, you actually see that you have like so then okay, so then the other assumption is, and that in this steady state region you have a different energy density, so the energy density of the steady state, and it can go with some fluid velocity u mu. In this talk is just the velocity, because we just work in. Okay, so there are several interesting things you could actually extend, but in this talk we assume like 3+1 dimensions, that the transverse plane is everything homogeneous and nothing moving in the transverse plane. You could actually relax that, and there are other works about that, but in this case there's only the fluid velocity in the x direction. And okay, so then there are basically two parameters you can actually solve for. So it's the energy density and the fluid velocity, and then there's also the parameter like how fast does the shock move, that determines like in the function x/t, these are really velocities. So it's really like how fast does it go. And also on the other side, so there's the shock moving in the hot direction, the shock moving in the cold direction. And well, there's 4 parameters, and there's energy conservation, momentum conservation, energy conservation, momentum conservation. There's also 4 equations. You can actually solve it very easily. And here
Wilke, sorry,
yes.
I have a very elementary question. At the shock, is this energy and charge conservation is valid exactly at the shock, or you have some forces there?
Yeah, exactly. So the constraints are really, so yeah, you have to think about this well, we do think about the shocks in like delta like distributions or something like that, but okay, you could smooth it out. Definitely energy and charge are conserved. I mean, we don't have any sources, so it's really assumption basically. So indeed, so if you have like, so if you know this energy density, you know this energy density, you know the velocity, then well, then you can check if energy is conserved, right? Because there's some flow.
Because
so
it's moving. It's moving.
Yeah, so it's a little bit, yes, because there's this velocity, so everything is moving to the right. So it seems that energy is not conserved, but actually, yeah, if you integrate the energy, it's just like energy is really moving from this part to this part. Yeah. And it is exactly conserved by assumption, by construction.
So you get an equation for the motion of the shock from these 2 equations, I guess.
Yeah. So yes, okay. So I put here this charge conservation too, but in this equation I don't show that. I'll show later a little bit more about charge, but you can also think about the whole problem just from an energy point of view. So yeah, it's a really unique solution. And there is of course a assumption here. So it's not that we fully solve the problem, right? Because it's ideal hydrodynamics. So here, if you assume that the only parameters, the energy density and the pressures, are really given by the speed of sound times the energy density, then the problem is fixed. That's kind of the statement here. And that you assume that there are these 2 shock solutions, by the way. Yeah, so there's really a lot of assumptions here, but actually, yeah, in 1+1 dimensions is actually exactly what happens. Okay, yeah, so I plotted it. I thought it was clearer, but just to show you, you can actually solve it analytically, mathematically, very straightforwardly. Also for the charge sense. Then, yeah, so I want to say a little bit more. So this the 2 shock solution. So you find the solution, but then if you actually check, and this was not so clear from the earlier papers in steady state and holography, but then later on, I think Chris Herzog and Jerome and others, they looked at it much more closely, and you actually will find that this solution is unphysical, at least in higher than 1+1 dimension. 1+1 dimension is what happens, but if you go to higher dimensions, what you'll find. So here you can. Well, because you know the flow, you know the energy density, you can look at the entropy density, assuming hydrodynamics so works outside of the shocks, and you can see how much entropy is generated. So you really look at the entropy as is E plus P over T with P pressure, T temperature. And then you look at so of course everything in between is by assumption in equilibrium. But then at the shock, there is actually but it's just a d mu s mu with s mu the entropy current, assuming this ideal hydrodynamics, the simplest way possible. And then what you will see is that the shock moving into the cold bath, maybe kind of intuitively, there's no problem. So actually, so ideal hydrodynamics, of course, kind of by construction conserves entropy. But because there's the shock, so a little bit related to Ian's question, I mean, energy is conserved, but entropy is not conserved because of the shock. So at that point or distribution, if you wish, you do create entropy. And actually, yes, so if you compute it, you do create entropy in this shock moving into the cold direction. And if you then also compute it, then it turns out that the shock moving in the hot direction, the entropy the second law of thermodynamics would be violated, so you lose entropy there. You can also compute it analytically, but I also show you the plot. And so this is it's actually well known. And yeah, you also see here that D has to be bigger than 2, because if D is 1, then CS squared is 1, and you'll see that actually there's entropy creation is 0. So it's only something which happens in higher dimensions. So this double shock solution we constructed is actually not a valid solution thermodynamically. And so you actually need to solve this. So this was an unphysical solution. It's a solution to ideal hydrodynamic equation, but it's kind of the time inverse, if you wish, in a way. And okay, so the second simplest solution you can basically do or imagine that it goes. So this is really what I think people looked already a long time ago, and it's called Riemann problem. So you still assume ideal hydrodynamics, but you don't assume it's a shock, but you assume it's a rarefaction wave. And a rarefaction wave is very similar to what I was showing before. So this is really as a function of x over t. So it's just everything is moving, but it just rescales. So if you have some shape which looks like this, then of course, if time goes on, it becomes wider, but in a linear way. So it's called a rarefaction wave. So it's a self-similar wave, if you want, and it only depends on this particular psi as a function of x over t. And well, okay, then I don't want to go into all the details. The equations, of course, if you plug in this ansatz, it's a little bit trickier. You have also energy conservation, but it's just the same way. You actually can solve it more or less, except for one transcendental equation, which you need one finite root to kind of determine the energy density at the point for the steady state again. Okay, and then I show here. Maybe I didn't say too much what the sky was here. So let's say, so the sky is really just a ratio between the hot bath and the cold bath. So you see here, we normalize it to 1 because it's a scale invariant theory. So we can normalize one scale to 1. And then the other one is just that then this ratio then determines all these solutions. So here are same guys, but here we then actually plot what is then actually a physical solution. So this rarefaction wave, that does obey entropy. That entropy should increase. Also, it's ideal hydrodynamics again, right? So also no entropy generation here, and there's a rarefaction wave. So the entropy is actually constant. Let's see. Should I say more about it? No, So I think, yeah, in a way, this you could think this is kind of the expected late time result, and we'll see more about it if you go beyond ideal hydrodynamics. Let's see. Questions about this, how the setup is in the energy density, then I'll say a little bit more about charge density, which is a little bit more complicated. And, well, this is how to solve it within ideal hydrodynamics with these ansatzes. Yeah, so if you include this charge, things get actually a little bit more interesting now. I was also studied before by Chris Hartog and collaborators. So then, of course, you have two ratios, right? I mean, we have this energy density ratio, and then you can, in principle, have a different charge density ratio in the left and the right initial conditions, N1 over N2, and cold over N hot, we call it. And well, here in this work, I mean, we could maybe quite easily extend it. Actually, it could be interesting, but we assume the energy density and energy flow remains exactly the same. So charge is just a perturbation. So in holography, this would be like saying no back reaction. So the metric stays the same, but you have a Maxwell field. In QFT language, we just say, okay, the charge density is really very small, but can still, of course, have very non-trivial dynamics. And that is actually interesting, because then what you get is that, well, so the flow of the fluid, the charged fluid now, the velocity is really determined by the energy density. I mean, you can maybe locally for a while you can have charge density which moves at a different velocity, charge density which moves at a different velocity than the energy density. But then because of friction, of course, very quickly they have to move at the same velocity. So within ideal hydrodynamics, they do have to move with the same velocity. And that's interesting because, well, I think you can maybe already imagine, like if you have a lot of charge at the right side and very little on the left side, and the fluid velocity and the velocity is determined, then there's actually no solution to the equation of the charge conservation if you assume that there's only one steady state region. So and one shock velocity. So actually, well, yeah, it's really because if you do assume that, then charge will pile up somewhere, depending on the ratio of these charge densities. So of course you need to be able to solve for any kind of this n1 over n2. So what actually will happen, and what so in a way is maybe intuitive, is that you have two kind of steady state regions for the charge. And they go with the same velocity as the fluid, as the energy, so it's Vs, but they have two different densities. So the green one here I find clearest. So there's like a lot of charge here, then there's rarefaction solution again, so then there's some charge flowing here, and then there's a different amount of charge flowing here. Well, with the same velocity but different density, and then again here. And this of course also have a non-trivial velocity, not trivial velocity. But okay, the velocity is always the same. And for illustration, like this orange curve, we put at a very specific chi value, which you can just solve for such that this doesn't happen. But this is only for a very fine-tuned charge density. There would be only one region. But in general, there are two regions, and actually you can have, if you continue to draw the extreme ratios, you can have like these continuous jumps here. Yeah, and I'll say
sorry,
more about.
I'm a little lost. So here in this, so you're saying there are regions where the energy density is varying, but the charge density is constant.
That's no, the energy density is constant. Okay, so yeah, we show these different solutions. So one setup is one curve here. So indeed, so the energy density provides these locations like the shock and the rarefaction.
Oh, okay.
And it's just that there is this region where the energy density is constant and flowing, but then in that region there are two charge regions. Yeah, you have to, because you don't really know how much charge is coming in, because that depends on the charge ratio and 1 over n2, which in this case we fixed the 2, 1/2 and 1. But you can also, we have some plots in the paper where we have different ratios. But it's so that's the thing, because the charge really flows on top of the energy density, and that's why these rarefaction and the place of these shocks, they are determined by the energy density, and that's also why you need this extra region. Well, one thing I've also been thinking about myself, and I'll show a little bit more in the results later on. It is a bit counterintuitive, perhaps, that you have like within this energy density that you have two regions of different charge density. So you would then wonder probably, like, why doesn't the charge not flow from the high density point to the low density point? Like, so in this green region, why doesn't it go from here to there? And what I'll actually show later on is that this is actually happening. So it's diffusion. So that actually is a diffusion process, because you can, of course, well, everything is flowing here, but it's a Lorentz invariant theory, right? So it's flowing at the same velocity everywhere here. So you can also go to frame just by boost, where everything is stationary and there are just two regions of high and low charge density. And it turns out then that this charge diffuses to the other one, but it doesn't go with a shock. So, and diffusion, as you probably know, goes like square root of d. So in the very late time limit, where everything is plotted as function of x over t, 1 over t is, of course, goes down faster than 1 over square root of t. So that's why this diffusion does not show up in this solution. This is actually a proper solution, but in the real world, this will diffuse. And I'll show more about that.
Mm-hmm. So one more small thing is this shocks, where the discontinuities. So here the x-axis is x by t, understand? So So they are always below 45 degrees. So there's they don't propagate superluminally, right? And this is something that yeah,
So
or, I mean,
well, what did you mean with x-axis?
I mean, the discontinuities, you get an equation for how fast they're propagating from these conservation equations, but they are not superluminal. Whatever your discontinuities are,
right. I mean, I would say they better not, right? But they can. We took the limit actually at some point in the paper. So let's see. So these are the shock velocity v and vh. If you send chi to 0, which is the most extreme ratio, well, what happens? So I think here it's CS squared, right? So that's the limit here. That's and well, the CS, of course, this 1 and here the limit is 1, right? Yeah. So that I think actually happens. So in the limit, but yeah, I mean, of course, this is also a physical setup, right? So you can actually put this. So if it would go faster speed of light, you would really violate.
But wait, I mean, if you take the limit chi goes to infinity in VH, then you get 1. Okay, that's fine. And on the other side, you get chi goes to infinity limit. You get CS square. Okay, I see. So it gets.
So that's consistent, right? So because in our paper
okay.
we assume chi is smaller than 1, which means H means hot and C means cold. But if you take chi bigger than 1, then the ratio is inverted. So then actually VH is VC and VC. So there is chi goes to 1 over chi, C goes to H symmetry.
Yes.
So okay, I mean, you did the check and it worked out. So
yeah. Okay.
Good for me.
yeah. And what is VS here? What is
so that's the velocity of the steady state.
At the steady state, I say.
Yeah, so there's the shock solutions, and then there is the steady state, which also has flow.
Yeah, exactly. Okay.
And the limits, well, we also computed at some point.
Okay, thanks. Yeah.
If chi equals 1 here, then of course the energy densities are the same. So you see that if chi is very close to 1, then there's just a very small velocity. Yeah, okay, and that's maybe useful to mention that in this double shock thing, that is the energy density of the steady state is just the square root of the product of the other two energy densities, which you can almost have guessed by dimensional analysis, but actually there are corrections which that chi is a dimensionless number, so you could actually get much more complicated functions. And as I kind of said, but not very explicitly, if you do this rarefaction wave, you actually have to solve numerically for this epsilon s. So you get an equation, but it's you can solve it analytically, and it's a little bit different than the rest follows from that.
Okay.
I'll show you more when I show you the holographic results for that. Yeah, so this is more or less how the charge density makes things a little bit more complicated and perhaps interesting if you wish. Then I'll go to holography, so if there are more questions about how this setup is and how things go in ideal hydrodynamics, I'll also happy to say a bit more about it.
So these solutions are also analytic. This solution is a function of x by t.
Yes, up to one of these find roots where you actually have to.
The one of those find roots. Which gives you the steady state velocity and the other stuff, like the steady state energy density. Okay.
Yeah, I think most of you are in a group working on holography, so I don't have a very long list of what holography is. I mean, there are of course several assumptions if you use holography. So you have like a QFT on the boundary, which has a large number of colors, and it's infinitely strongly coupled. So it's strongly coupled QFT, and then the nice thing is that you can actually look at this boundary, the dual problem in holography. So where you have like classical gravity in the bulk, and then in these limits, and if you describe n as force of Young-Mills, then everything becomes very simple in a way, because this classical gravity finds them with one extra direction, which you can think about as energy scale. So yeah, for that I just put the action here. I mean, we work with this charge thing, right? So as I said, so you have really like this Einstein-Hilbert plus a Maxwell term, where this E, so it's kind of saying the charge density, and in this work we always assume E is just infinitesimal, so you expand all your equations in E and only look at the leading term. Although we actually have some codes which work not non-linearly in E as well. So it's also something you can definitely do, but we didn't. Let's see. So yeah, and of course, well, one of the greatest strengths, which I'm sure most of you have probably heard, is that holography you can really solve is with perhaps the only tool really where you have QFT at strong coupling, where you can study real-time dynamics fully far from equilibrium from a kind of a first principle point of view, because this duality holography is assumed to be in this easy case of NH4 super young Mills to be exact. So if you have like Einstein equation and gravitational waves and all these kind of things, if you solve them numerically, say, then this really should give you like the time dynamics also of the strongly coupled QFT. So it's really very unique. And okay, I mean, I showed you a bit of this rarefaction and shock solutions, ideal hydrodynamics. But okay, with this setup, actually, you can go and solve the full far from equilibrium problem much beyond hydrodynamics. And that's why we think this is really very interesting. One thing I put here is like, this extra direction is energy scale. So there's usually a black hole horizon. I mean, I put here just some illustration. I mean, in our case, it's just a black brane, which is constant and has these kind of kinks like the shocks in one direction. So in one direction is non-trivial dynamics, right? There's left and right. In the other directions, it is trivial. What actually works is that as you go to this black hole horizon, so there's like UV scale near the boundary, and in the black hole horizon, it's kind of the thermal scale. So this is really the depth of the horizon really set by the temperature. So also this. So this is actually not a very good illustration. Like we would have this hot horizon, which would be higher up, and the cold horizon would be lower. And then there would be some kind of intermediate regime, which we could actually plot. And also, for instance, what happens is you can have very fine details here, but then typically what happens, everything is kind of smoothed out if you solve the equations towards the horizon. So everything would be, if you have a shock at the boundary, which we could have, then you would have something which is like smooth on the scale of 1 over the temperature at the horizon. So that's kind of how this kind of intuition works with this extra direction. Well, okay, so that's a very brief glimpse, I have to admit. How do we do this in practice? So in each, so we solve Einstein-Maxwell equation, Eddington-Finkelstein ansatz. This has first been solved by Jessler and Jaffe. They have a long review paper on how to solve this. And as I kind of mentioned in the very first minute, is that you can actually use the same system where you collide shock waves. It's the same amount of symmetry with this transverse directions being completely symmetric. And yeah, so how do you solve this? You have the action, and then you have this ansatz for the metric, which Eddington-Finkelstein ansatz, and it's actually a very smart ansatz because it simplifies the equations a lot. It's just a gauge choice in a way. It's also a gauge choice for the electromagnetic field. And yeah, this Eddington-Finkelstein ansatz just means, of course, that this is to the RDT term, and there's no dr squared term. It's just the ansatz. And then here we call Z the direction of, well, it used to be the shockwave collision direction, but now it's just the left cold direction. And you see that, for instance, what will be quite important is that there's this function B, which rescales a bit differently the transverse direction and the longitudinal direction, the longitudinal being the hot-cold direction, which means in particular you can have a different pressure in the transverse direction and the longitudinal direction. So you can go beyond ideal hydrodynamics in that way, and then even beyond viscous hydrodynamics. I didn't put explicitly all the dependencies, but you should imagine that all these functions like C, G, S, and beta depend on R, T, and Z. So R being the holographic direction, time, and Z is the same. So yeah, you really have, because we used to have 1 + 1 dimensional problem, now it's a 2 + 1 dimensional problem. And okay, then the initial conditions are more or less the same, right? So for you kind of, if you know then by holographic dictionary, if you know the whole metric, you know the energy density on the QFT and all these kind of things. So yeah, we now have this cold, hot direction at T = 0, and we can actually just put the energy density and the charge density, these fields to be what we would like. And yeah, I set here up to subtleties, and there is a little bit of a subtlety here, but it's actually not so important in this work, because it's true that these are conditions you have to specify, but there's also this function B, and once you specify B, you actually, by Einstein equation, to determine S, G, and C. But this function B, as a function of this R, it's also a free function as an initial condition you also need to specify. So there's lots of work studying that, and for the shockwave collision, you need to have a very particular B But actually in this case, because it's like we are interested in more or less late time steady state region, it doesn't actually matter what you choose, because if you choose something which is a little bit crazy, then within a time of 1 over the temperature, being either the cold or hot temperature, that's then that's something you could study, the system will relax to kind of it will kind of thermalize or hydrodynamize, go to hydrodynamics. So on the time scale of 1 over the temperature, it matters a lot what you choose, but not on the time scales we are looking at. And in this work, we just chose p equals 0 as an initial condition. That's the subtlety I'm referring to. Well, let's see. So, okay, then I also don't have time to explain how to do all these numerics. It's really explained very nicely in this paper by Paul and Larry. I also have my own code on my website and then explain it a little bit in my PhD thesis a long time ago. What is very nice about this Eddington-Finkelstein ansatz is that you actually get a nested set of equations. So I just for kind of a little bit how it looks like a lot more or less, I put here the Maxwell equations. Einstein equations look very similar. They're a little bit longer, but not that much. But the nice thing is you have these Maxwell components like F mu nu, and then with some component R, T, and Z. So there are several combinations you can do. Primes here are R derivatives. Tildes are kind of C derivatives, but not quite. Dots are time derivatives, but also not quite. So it's kind of, you have to do these transformations. But the nice thing is that once you know, in this case, FRZ, that's an initial condition in this case, you see there's an equation for FRT here, because assuming you know all these metric functions, which we do by Einstein equations. It's a nested, it's called a nested set of equations. So you know FRC and all the other functions. Then this is FRT prime. So it's a differential equation in the R direction for FRT. And actually the important thing is a linear differential equation for FRT. So you solve for that. It's actually just an ODE, so you can just invert a matrix numerically. Then you know FRT, and as an initial condition, you know FRZ, and you can see you can solve for FTC. So FTC is here, FTC prime is here, and it could be nonlinear in all the other functions, but it's linear in this FTC. So you have again a linear equation in the R direction, just simple ODE. Then similarly, you solve for this FRC dot. So now the dot is a time derivative, but we don't know the time derivative. We want to find the time derivative to solve the numerics. And yeah, I think there's so this equation for FRC dot, and you can solve that. And once you have FRC dot, you go to this equation and you actually find out the real time derivative instead of this dot time derivative, because you know C and you know the H, the R derivative of this function. So this is kind of a little bit in a nutshell how this numerics work. I mean, these equations you have to do, of course, with Mathematica. They're very long. There are some subtleties too, because the boundary, all these equations, they diverge. So you kind of need to do this near boundary expansion near the boundary and subtract these divergences. So that's kind of see some subtleties. But yeah, and actually, so for the shock waves, to get everything stable, and there's some vacuum parts, you need to regulate it. It's actually not so easy to solve. But for this thermal case, it's actually relatively straightforward, because there's a horizon, cold horizon, hot horizon, and kind of smoothly connected. So it's a relatively stable system, and this was actually not a big problem to solve. Yeah, okay, so if there are questions about how this relates to the other part, or want to know a little bit more about how to solve it, then you should ask now, and otherwise I show you more or less what then comes out of these kind of simulations, or if you want to know more about how these functions are related to the energy densities. Questions about that? I mean, I realize I don't go into full details about how to actually solve it. I mean, this is just how it looks like, and how the initial conditions, and you run your code, and then you extract the energy density as a function of time. Yeah, so this is actually how it looks like. So this is really kind of this picture I showed you on the very first slide. So you have like some initial condition at t equals 0, the charge density, and how it goes as a function of time. You just keep on plotting the charge density as a function of this z coordinate. You have to realize that if I'm showing you here like the charge density or the energy density, it's really extracted at the boundary. So that's kind of this boundary holography QFT. So there is in the numerical code, there is this extra R direction. But yeah, you only use the boundary values of your your fields to really make this plot. So this is extra direction you don't really see in these plots, because these plots are the energy density, charge density of the QFT. So the energy density, for instance, in the bulk, typically we just assume vacuum, or with Maxwell you can maybe have like some energy density of the electric field, but it's a very different kind of energy density. There's maybe energy behind the black hole horizon, but so I'm just stressing that these energy densities and charge densities are really of the QFT. So how to read these plots? Okay, so it's we also just like to make these colors because it's pretty, of course, or something like that. So this is this Z direction. M is a scale we set for this, just the hot temperature basically. And then all these curves are just different times. So you really see t equals 0. We actually don't have a true delta function at t equals 0, right? So you see actually there's a tanh. If you have a true discontinuity, the code would hopelessly break down. So you really need to kind of smooth out this initial condition. And we actually verified in the paper that it doesn't affect the results. And then for later times, you really see that this initial condition, that you see that all these curves are moving to the right. So there's really, which really means that there's energy indeed flowing. And here you see it even more clearly. Maybe there's the shock going to the left as a function of time and creating really this steady state energy density.
Wilke, I have a question. I have a question about this plot. So there is some kind of a left-right asymmetry which is slowly building up. What causes this?
Yeah, that indeed is a very good thing to notice. I mean, some people think that there might be left-right symmetry, but there actually isn't, right? Because the one is hot and the other is cold. And there is, of course, the symmetry if you exchange hot and cold and you do chi to 1/chi, like what we were discussing before. But it's really exactly the same as this picture. So there's no left-right symmetry here at all. There's like energy flows from hot to cold, and the flow is also to the left. But there is left-right symmetry.
Actually, my question is not about exactly the symmetry. Okay, so the question is about, so you have something halfway in between, probably, or no, it's not really halfway. So if they are very far apart, if these two differences are so there's a plateau in between, and as the plateau is growing, so you are producing this asymmetry more and more. But if they are very far away from each other, they should be looking very similar unless the differences are not the same. The ratios are not the same. Probably there is asymmetry in the ratios which causes this.
Yeah. You're definitely right about it. But there's this rarefaction wave over here, or at least more or less, and then there's the shock over here. So there's much. So if you folks read on the latest time result, I mean, it's also maybe a little bit difficult to see, but this is that curve here. So it really looks like a shock here in a way, but it's smoothed out. Then it's constant for a long time. And then here, indeed, it goes up in a smooth way.
Like a rarefaction wave, okay. Yes.
It is really like a rarefaction wave. So it is really looking qualitatively in a way, at least very similar to this one. So the blue one here, for instance, depending on the ratio, I think you see a very similar thing like what you're saying. If there's hot bath, and then there's a long constant region, and then there's a rarefaction wave, but it's not symmetric. And I think it should not be. I mean, if you, of course, there's parity symmetry, but since we assume that the hot bath is right, then that's breaking this parity symmetry.
I see.
And okay,
no,
I mean,
I'm saying that if you just had like, if they're very far apart, I mean, okay, you're saying that somehow the rarefaction wave is initialized at the early time, because what my concern was that because these two are very far separated from each other, you would expect that that this, I mean, there should not be so qualitatively different behavior at these two ends. But maybe what is it is initialized at early time when the shocks are not that far apart, and when these two discontinuities are not far apart.
Yeah, I don't think it's about the initialization. So nothing here is sensitive to the initialization. It's just the shock and the rarefaction, they are far apart, but there is a physical difference if you go from hot to steady state or from steady state to cold.
Okay. I see. Okay, there's a physical difference that way. I see.
Yeah, because the flow here is also to the left. Yeah, so I think that is important.
Okay, thanks. Yeah, okay, I see.
Yeah. So here you're, in a way, I mean, of course, if you're feeling physically, then here you're pushing, in a way, energy into a cold bath, right? The shock really is like hot energy being pushed there in there, whereas this rarefaction wave is more like how do you get pulling energy from the hot particles.
I see. Yes.
It's quite different. Yeah. And okay, so these are the full
Thanks, yeah.
radial CFD results. And of course, I'm saying here there's a shock and here's a rarefaction wave. And actually, in this plot, we show you kind of these analytic or almost analytic solutions in dashed what I was showing you before of the Riemann problem. So you see here that there is this shock here, and there is this rarefaction wave here. And you actually see it's not exactly the same. And we study this a little bit more detail on the next slide. So you see there's actually quite significant differences. And this is really, I think, because this ansatz of the rarefaction wave, at least on these time scales, is not exactly right. And also for the shock. I'll say more about it in a few slides. For the charge density, then, yeah, so actually, that took a little bit of maybe technical effort to kind of get this nicely, that you see have the charge density 2 of these plateaus, and then this rarefaction wave. But I think you definitely see it. I mean, if you look at the 3D plot, you definitely see 2 plateaus, and there's no this contact discontinuity here. And it's already in the next slide. No, not yet. In 2 slides, I'll say more about this kind of contact discontinuity, which I argued first should be there, and then by this diffusion argument is not really seen so explicitly here. One way to make this analogy with the shock rarefaction wave much closer is of course not to plot it like this as a function of time, which gives beautiful plots perhaps, but actually I think what's probably more insightful is to plot it again as this function of size and its rescaled coordinates, and then different colors, there's again different times. And then the question is really like what happens in very late time. So first you have the shocks, and it's like non-trivial dynamics, but actually if you do it in the rescaled coordinates, well, you see here the shock is pretty constant. I'll say also a little bit more about it. But then, of course, if you rescale it because of this 1 over time here, you see that if you look at the shock as a function of time in its rescaled coordinates, this green one is our latest time result, it really becomes closer and closer to a true shock. And even if the wave is constant, and of course, because of the 1 over time, it would actually become a true step function here. And then actually the questions here, I also noticed, I think I said that these holographic results and this dashed line is not exactly the same. And then the question is like, is there some mistake somewhere or something like that? And it's not so clear. Like if you look at this rescaled coordinates, if this green line in late t infinity limit goes really to this rarefaction solution, which looks like this, I think we thought it could, but I think it's not exactly resolved. It will. It's basically the only sensible answer because okay, that's the unique solution to ideal hydrodynamics. But yeah, there's some viscous corrections. We don't exactly know that. And here I plot the same thing for the charge density, and also here you see to go maybe to the shock, and maybe also the green one would go actually to this discontinuity at infinite time limit, but it takes a long time, which is one of the conclusions of the paper. Good. Well, then the thing I didn't show before was the velocity of the fluid. So it's negative because it goes to the left. So here's velocity for different times, and also you can compute again the shock rarefaction wave velocity. And what is interesting here is that the shock and shock rarefaction, they give very similar steady state energy densities and velocities. It's the difference between the dashed line and the dotted line. But then if you zoom in here, so this is just a zoom of the upper plot, then you see that actually very accurately at late times, it goes to the shock rarefaction wave velocity, but not quite. So there's like small deviation, and we think we understand this by looking at hydrodynamics and looking at viscous effects. So going really beyond hydrodynamics with some kind of with some eta over s. I have one slide in the backup slide if you're interested in to hear more about that. Good. Well, also I'll interrupt me if you want to know more details. Otherwise, I just show you a few more things like what we try to figure out. One of the things I thought myself was quite interesting was this diffusion and this contact in discontinuity of the charge between this 1 and 2 regions between the steady state. And for that, actually, yeah, you can show this in a very simple setup, which is probably trivial maybe, but you just put constant energy density everywhere. So energy density is just 1, and then different charge densities, and do very same same run basically in the numerics. So this is the initial condition, and then you really see that it kind of diffuses. So the charge goes from the high charge to the low charge. And then of course you can look at the width of this kind of distribution. If you take the derivative you take the derivative of this, you get kind of Gaussian, and you take the width of the Gaussian, you can see how much it widens. That's what's done on the right. So it's a function of time, the width of this distribution, and you really see it's growing perfectly like square root of t. So well, I mean, that's kind of trivial, I think, but since we reproduce this, it really explains, I think, why we don't have this delta function here, but we really have this smooth diffusion evolution here. And if you would run it to really t is infinity, then you would really see that it would actually look much more like a true contact discontinuity. So I think we can actually see this in this way, even though the simulation is a bit harder to run longer and longer. It would need much more computational time and would maybe at some point become unstable. Okay, another two things I think I wanted to maybe then show you here. So this is a relatively simple computation. So this is divergence of the entropy current, same as I said before, entropy current just by looking at the energy density plus the pressure over the temperature, taking the covariant derivative. And then you get this for different times again. So here is the rarefaction entropy generation, and here's the shock entropy generation. And then of course, well, what you see, for instance, in the red one here, you have the shock, and then it's 0 for a long time. So really meaning that ideal hydrodynamics is very good approximation, and you don't have any entropy generation. And then there's a little bit here for the rarefaction wave, but it's quite small. And then of course, interesting questions like how much really entropy is generated then. So you can integrate divergence of entropy current from the left and on the right. And that's what done on the plot here. So you're really just integrating basically the area under this curve, and that's kind of the entropy generation left or right, or shock rarefaction. We labeled it here. This is the shock, this is the rarefaction. And you actually see for the rarefaction wave indeed, so there is a little bit of entropy generation here, but you actually see it goes to 0 in a very good fit with a power law. So at late times, this rarefaction wave is really very close to ideal hydrodynamics, which would not have any entropy growth. For the shock, it's actually conjectured. If you look at our analytic formula here, I mean, we actually had this entropy generation for the shock going to the cold direction, and you can actually compute exactly the size, what it is, according to the Riemann problem. And it's a little bit of a puzzle to some extent. I mean, if you compute it analytically, like I showed on slide 5, we got 6.1. And okay, here we showed as a function of time, and well, 6.1 is about here. So it could actually go to 6.1, I think. But if you fit it, like 1 squared t, and then with some constant value, you see it would maybe probably go to a constant, but not quite to 6.1. So it could be just the numerics that would actually go to 6.1. But yeah, so this shock keeps on generating entropy. The last thing I think I wanted to show about the results, and also about the shock, which keeps on generating entropy. Then one interesting question is the shape of the shock. And well, of course, here it looks pretty constant, the shock moving to the left, but it's not exactly. And one nice way to show that is take the time derivative of the energy density. So because the steady state, of course, the time derivative is 0, so you really see the time derivative really gives you the shock and a rarefaction wave. This shows the time derivative, and then you also much more clearly see the shock, and also that shape change a bit. So here it's higher and narrower, and it really widens. And then of course it makes a lot of sense on the right here to plot as a function of time the width of this distribution. So it's like full width, half maximum. So you take like the maximum, and then what's the width at half of the maximum. And also there, yeah, actually, if I have longer numerics would be beneficial, because its points are the numerics, and then there are some fits. So actually, you see that what is a log scale, this linear scale. So this log MT fit, the blue one, is really very good. There is like initially, I think it goes more like square root of t with some offset. So that was in the initial dynamics. I think it's also expected, and you also expect that it doesn't last. But there's this paper by Andy Lucas, and like I was already saying, and they kind of had the idea, and had some arguments that at least in hydro, the shock would become more like a solitonic object. So it would not be like a true discontinuity, but it would be like some fixed fixed kind of solid tonic thing, which would imply that the entropy generation would go this width would go to particular objects which would be constant in width. So we also try to fit that motivated by this work. So this is kind of this green curve, which is a constant, which would go exponentially to this constant. Yeah, and in fact, these green curves also could fit. So of course, it could actually go to solid tonic objects. So that's something which is not resolved from this work. Okay, well, yeah, then I have like this 5 slides about this new paper, but I'm also very close to an hour, so maybe I'll leave that for later. Or what do you think I am?
Well, it depends. If you want to say something, it's fine because we have time, but we can also take more questions for the moment and, on this.
Okay, they definitely have your question about this, and
yeah, I have one question. So in the context of this hydroderivative expansion and all that, so could you say something that is growing logarithmically? Does it say something about something new about this derivative expansion in hydrodynamics? Could you infer something?
You mean if within hydrodynamics this would grow logarithmically?
No, my general question is that you have this, we have a derivative expansion, and this is somehow your solution is an exact solution where you have all orders and derivatives in. So what I'm trying to say that the shape, like the growth of the shock, right, should be. Could it say something about how do we get it from some kind of infinite order hydrodynamic theory? Or is it some way we could try to understand?
So we try to understand that a bit more. So that's a nice question because so I should have probably put it in the main slides. So the approach, I think one way we could say something about it because here, well, we of course have to meet the full nonlinear equations, and so here there are 2 things I'm showing. So it's again the shock moving to the left and the rarefaction moving to the right. And what I'm showing here is really the transverse pressure over the energy density in a local rest frame. So both of them are in the local rest frame. And of course, if everything is ideal hydrodynamics, then by assumption, this should be 1/3. So this would be this green region. And also you don't see any difference between hot and cold because, well, of course, the energy density is bigger here, but the pressure also, because that's what ideal hydrodynamics means. But as I said, there is like longitudinal transverse pressure. So it can deviate, that if you can have less transverse pressure with more longitudinal pressure, and that's then a deviation from ideal hydrodynamics, which could be explained by these viscous hydrodynamics and even higher orders, like you were saying. And then of course you could maybe try to resum it and the way to view our solutions, then maybe the all order resummation of hydrodynamics, if that would apply, right? If you could resum it. So here you see the deviation from ideal hydrodynamics, and then we also looked quite carefully at the viscous hydrodynamics, so including eta over s, but not more. So you see very clear deviation from ideal hydrodynamics. This is solid curve or shock here. So this is really like the difference between pressure from we compute an ideal one, and this blue region here is the same as this deviation here. And then we looked at the same difference between viscous hydrodynamics. And you see, okay, so it's much smaller difference, really much smaller. And yeah, so almost all of the dynamics you can I think really be explained by viscous hydrodynamics. So you have some non-trivial gradients which you can compute, and that gives you some viscous hydrodynamics, and that gives you some pressure, and then you have your equation actually closed. And you even see that okay, so here the blue one, it's a little bit bigger than the red one. So, and then well, your question would be to some extent, I think, if you include second order corrections, it will become even smaller if you compute everything. This is, I think that's kind of your question.
Yeah, thanks a lot. But then I have what is puzzling to me, because there are reports, I think, if I understand correctly, that if you introduce just first order hydro, you get some acausal behavior of shocks. So
Yeah, that is a good question. So if you have first order hydrodynamics, you don't introduce any other terms, then typically if you try to solve these equations function of time, you can get, if you have like a very sharp gradient, you can get shocks that move faster than light. That's not what we're showing here. I mean, if I do viscous hydrodynamics, I'm just trying to compute the transverse pressure from the energy density and the velocity like we have in the full solution and with the viscous solution. So I'm not solving hydrodynamics here. I'm just comparing how the solution would have looked like in hydro and how it looks like in the real holography. So that's why we don't have this acausality problem. I also have to note that this acausality problem is not, I don't view that as a problem of viscous hydrodynamics because it only applies for very small wavelength modes. So K being really large in the gradient expansion. So you're already outside of the regime of hydrodynamics, which just means the gradient should be smaller than 1 over the temperature. So I know about this causality problem, but it's also a bit of a numerical problem if you try to solve the equations. And in this case, yeah, since we don't solve hydrodynamics, we don't have this problem.
I understand, but then but still the fundamental thing remains why it is working. I mean, in the sense that there should be some way. I mean, if you just take the original viscous hydro, and then you might be able to do something to it so that it can still reproduce this behavior to a good approximation. The question is what exactly you need to do up to it.
I mean, yeah, so we didn't try that, but obviously there are hydrodynamic codes which could solve this problem maybe with some eta over S1 over pi, something like that. And then what you do, of course, is you introduce second order terms that then counteract this acausal behavior. So I think there are stable codes which could solve this, and probably they'll give very similar results because the deviation of viscous hydrodynamics and the true solution is so small, as long as the second order terms are, of course, not dominant. But yeah, I think the gradients here get smaller and smaller also because these shocks get wider and wider. Yeah,
I see. Quite interesting. Actually, David Matthews gave a talk in on our conference. So he said not exactly what you're saying, but there were this first order like bubble wall between two solutions, and then he was able to he showed that. If you do MIS, it doesn't work, but if you do second order hydro, it quite fits this description. And
yeah, that is very interesting. Yeah, in that particular setting, I think the MIS, if I'm not mistaken, at least for these conformal kind of velocities, the first order is actually 0. So the second order is actually the first non-trivial order. And indeed, if you then include that, then suddenly everything works perfectly, which is very interesting. It's but at least the message I took away of that, as far as I remember, is that you need the first non-trivial order, and then usually it works, and the higher order terms typically don't need. But I'm maybe confusing two papers of David. This bubble wall velocity is actually indeed very interesting because it is a very similar setup. It's also kind of above moving. So of course, then you would have, if it's a spherical thing, you would have like something.
But you don't have two different equation of states, unlike he had. If you have same equation of state.
Yeah, they're definitely different. Well, yeah, the equation of state in our case conformal, so it's trivial. So we could, it would actually be interesting to this same setup with the bubble wall thing. So there, of course, you have this instability, where you have like a high energy density and low energy density region, and that causes these shocks. And one thing I thought interesting about that work is that in this case, we have as an initial condition the cold energy density and the hot energy density. But in their case, you only have the hot energy density as an initial condition, and the cold one is actually determined dynamically because it goes to it's unstable, the hot one, so it goes to the cold one, and then there's also the shocks moving out. But you have one initial parameter less. I'm still a little bit confused. Like the Riemann problem, you cannot formulate in that case because there's one parameter less as an initial condition. But of course, you can put it in holography and run it dynamically, and that's exactly what they did. And I think, yeah, that's very interesting. And you could use more or less the same code, just use scalar field, scalar potential, and then you would get that out.
I think the final solution itself was described by second order hydro, just the final bubble wall, like something like that. But actually, I had a different question also. If in your setup, this logarithmic growth, can you get it from first order hydro or any kind of hydrodynamic? How the shock is width is expanding? Would you be able to get it from some hydro-like description?
I don't think so, because they studied this more or less quite carefully in this reference where they indeed do some, but that was tricky because they did do some back of the envelope estimates, because at late times you do expect the viscous hydrodynamics describes these shocks because the width grows and the temperatures are always constant. So the gradients, they basically get smaller and smaller because the shock kind of grows. So at least you can assume that. And at some, yeah, I think there is an issue there. Now I remember. So actually, yeah, if you assume that the width keeps on growing, the gradients get smaller and smaller. And that in particular would mean also the entropy generated gets smaller and smaller. But I think there's kind of a lower bound on the entropy generation, because you just have, it doesn't really matter what happens at the shock. You have like energy density here, energy density there, and there's flow, and it's like a finite size. I think you run into a contradiction if you assume it gets wider and wider, but not large on the scale of the rescale, because the entropy generation you can estimate and using viscous hydrodynamics gets smaller and smaller, but you can actually estimate the entropy production and it's a finite value. It's kind of this why the estimate 3.77 here numerically, but it would be analytically like 6, or you can change this with different viscosities. But you do, yeah, so you run into a contradiction there. And that's, I think, why they argue, well, this logs fit is very good, but then, so I first thought it was definitely logarithmic growth. But then I read that paper more carefully, and I think I got convinced that probably this green curve might be the better solution for that reason. Yeah, I could try to, I have to try to repeat this argument. It's in this paper. We say something in our paper as well.
I see. So this is a paper by Doyle and Schee, as interesting. Okay. All right. So more questions to Wilke? Okay. So good. So maybe about the other thing, we can have you or Christian giving another talk to us.
Yeah, I think it's better. I mean, I didn't know how fast it's going, because for some reason I could flash through. It's interesting, but
yeah. Okay, then thanks a lot, and we can then continue our discussion off the record. So let me turn off recording.